Thessaloniki in 19th Nanoscience and Nanotechnology Conference, which takes place for 10th time, 10 years, here in the Palace Hotel in Thessaloniki. Actually, we use a picture I just noticed today from 2020. Here, physical presentation. As you in Thessaloniki or in the capital of the north of Greece, the second city in the country. Thessaloniki took the name from Alexander the Great, Thessaloniki, 23 centuries ago, and the conference takes place both in live and virtual. I gave the same picture you saw in the beginning, virtual supported by the AlphaView platform. And here I have to say many thanks to Fosteropoulos Kostas and Fosteropoulos Nikos. He gave us the opportunity almost three years ago, to use this platform. You know this platform we used the previous year, local for some presentation, and this it was very ready, let's say, in April 2020 to decide that we can make the conference virtually and live. So Kostas Fosteropoulos is somewhere here, we'll see later. So some statistics how things change progressively the last 3 years. Sorry, it's going here. You see how change the percentage with live participants and the virtual, how change this one from year by year. Today, this year, you are almost 77% of participants are here, not only in Nanoscience, Nanotechnology Conference, but in the whole event, on Nanotechnology event, because Nanoscience and Nanotechnology Conference is part of Nanotechnology Conference, and you will see some details for this later. Okay, just here you can see that the conference, the Nanotechnology event, this is not good. Involves not only this conference who started today, but also involves the school who started on last Sunday, 2nd of July, and will finish next Saturday. Also involves the conference ISFOE, which deals with organic electronic materials, started yesterday, and yesterday at noontime started also the expo. And you will see tomorrow another conference who started 5 years ago and deals with also with 3D printing and 3D bioprinting. All this together with other events take place in parallel in the same umbrella. So this conference involves 4 well-established workshops. The first one is dealing with, let's say, with inorganic technology or inorganic mostly materials, and deals with nanoelectronics, photonics, phononics, plasmonics, and nanoenergy, but all based mostly on inorganic material. This is the base of this workshop. The second workshop based on nanomaterials, nanofabrication, nanoengineering, nanoconstruction. You have a mix also here of materials of inorganic and organic material, all polymeric materials. Nanostructures and nanoparticles are also several of the topics of this workshop. And while the third one deals with a subject that started almost 17, 18 years ago, the nanomedicine, the area where the modern biology with nanotechnology and medicine are met. So you have subjects related to nanobiomaterials, but also nanoparticles for medicine, clinical applications, 3D printing, bioprinting actually, regenerative medicine are some of the topics of this workshop. And the last conference of this workshop, which runs also in parallel with other workshops like the workshop number 3 of on nanomedicine, is the workshop on biosensors and bioelectronics. It's a new era started approximately 10 years ago. Is the era where advanced materials, modern electronics, nanotechnology, biology, and medicine meet together. And of course, diagnostic is some of the main subjects of this workshop. So many thanks now to our distinguished professor. Today is the plenary session with 3 distinguished professors coming from Germany, Professor Paul Blom from Max Planck Institute. He is going to talk mostly on organic light-emitting diodes. Professor Lorenzo Moroni from the Netherlands, University of Maastricht, he is going to talk about the textile scaffolds bioprinting, and Professor Jenny Nelson from Imperial College to talk about molecular electronic materials. But also, many thanks, and these distinguished professors from various places. I'm not going to say one by one. Some of them are already in the room. Some others are coming. So this is the keynote speakers, and of course, many thanks to 150 distinguished professors, young scientists, people from industry, which are invited to give the talks. Not only in this numbers are also our numbers in total cumulative numbers from those related to other conferences, I mean the organic, electronic, and 3D printing as well, or other events which included in the program of Nanotechnology 2022. Also, you have the opportunity, and many thanks to 36 European projects will be presented. They will present the results. Some of them, they have the meeting, annual meetings or review meetings. More than 150 million correspond to this cumulative budget of this 36 project, coming from 130 organizations. And I hope to enjoy to see this consortia, the people from these projects to discuss. There are a lot of opportunities here in Europe, but also internationally, to build a new consortia. This conference is quite an interesting point of networking in order to build such a kind of consortia. Just a few words about the history of this conference. Started, as I said, 19 years ago in Aristotle University. The first workshop at that time, it was during the first graduate from nanoscience and nanotechnology master degree of Aristotle University in 2004. It was in physics department of Aristotle University. You see around 50, 60 people at that time. It was started this conference, and since then, 2004, he used to make Professor Damjanovic. It was one of the people, maybe there in this picture, and Ivanka from both professors in Belgrade, also evaluators of this degree. Also Professor Kusula, he is not here, and Professor Berkeley. He was in weddings of his daughter last Sunday, came from San Francisco. They were the evaluators of this nanoscience and nanotechnology degree of master degree in Aristotle University. And the first graduate was Professor Sarakinos. Later today, he will give an invited talk. He's in Sweden now. So this was the first workshop in 2004, and then for almost 9-10 years, this used to take place in Aristotle University. And in 2010, actually, it was the 10th conference, moved to this peninsula, in the third peninsula, where met and took place two conferences. These conferences and another one which started 2 years earlier, it was the ISFOE, International Symposium on Flexible Organic Electronics. We organized these two conferences and the school at that place, and this was the last year you made the two conferences outside of the city, and then moved to Thessaloniki the last years, and the last 10 years this conference takes place here in Porto Palace Hotel. So this is the main event. The main event, the nanotechnology, with one conference, the second is for the third one, it's pity, the I3D, the International Conference on Nanoprinting, and this is also in detail the conference, what involves in the conference in the ISFOE, where you have also 4 workshops, just to say. It deals mainly with organic stuff, or organic semiconductors and several inorganic materials, but all of them are mostly printed, and some of them are vacuum technologies, based on workshop on organic large area materials, organic photovoltaics, perovskites, OLEDs, organic thin film transistors and sensors or biosensors, wearables and Internet of Things, in parallel with the common special workshops, like the workshop on agrovoltaic this year. We introduced to this conference a special workshop on agrovoltaics, especially for energy, but also for light and sensors in agrovoltaics, the printed sensors and integration of battery and photovoltaics, the workshop on open innovation and standardization running from several of the European projects, computation modeling and materials device and process, which is common in all conferences, and the workshop on real-time and in situ and quality control for nano-manufacturing. So these special workshops run in parallel with 3 conferences, and the third conference is this one, which started almost 5 years ago. Of course, deals on mainly on 3D printing techniques and 3D bioprinting techniques, also on tools, new tools and metrologies, equipment, laser, and digital and additive manufacturing. So around 40 exhibitors are present the results. There is a large also exhibition on organic electronic, let's say, photovoltaics, organic photovoltaic third generation, OLEDs and sensors exhibition. Also, just not to forget, during Wednesday, tomorrow, every year in this conference takes place this matchmaking event, the B2B event for technology transfer and business partnership. The aim of this event is to bring together the people, either for academia and research or from industry, to talk and to build consortia or to talk about technology transfer for applications. The school, as I mentioned in the very beginning, started on Saturday. It's a school where 3 days you have lectures, the last weekend, Saturday and Sunday, and next Saturday. Between the 5 days, the students follow these conferences. They have to choose in one of the directions, either in nanoscience and nanotechnology or in organic electronics stuff, relate mostly with conference, the ISFA conference, and nanomedicine, which is a mix of these three, relate also with biosensors and bioelectronics. Of course, the conference has also these entertainments. You used to have a second one, which was the except of official gala dinner, where all people from all conferences and the school are invited. Take place after the plenary session, which is today afternoon, around 20:30, 8:30 to 9 o'clock in this roof garden, this hotel, this roof garden. So all of you are invited. I start to say that we have another event. It was the beach party every Wednesday afternoon. You cancel this one in order to take some protection, let's say, against the COVID and to protect ourselves. So many thanks to organizer, Professor Hadjioannou, Professor Gianellis, Professor Kovopoulos. I mentioned he is here, but he will connect it on because he has the weddings last Sunday. Professor Silva is here. Professor Tanaka from Japan. He changed university. It's not Yamata University. He is in Okinawa in Japan. And Dr. Gravalidis, thanks a lot. Where is Christophoros? Is somewhere here. He is the head of this conference. Many thanks to these people. Of course, many thanks to our exhibitors and our sponsors. They help a lot in this conference, not only the NN, but also the whole event, the nanotechnology event. And of course, many thanks to you. And I hope to enjoy the conference, the meetings with the other, and networking with the other conferences, and meeting people from the 36 projects, European projects, and I hope also to have the time to enjoy the life in city. These days there are many people in the city. So you're welcome to Thessaloniki, you're welcome to NN 2022 and Nanotechnology 2022, and I hope next year to be all people here and less people to be on virtually to be connected. I suppose that it will remain this virtual connection or connection with not physical way, at least for some invited people, because it's a new way of life we discovered during this possibility that help us in some cases. But in any case, we hope next year from 70% of participants here in live presentations to be reach more than 90%. Thank you and welcome to Thessaloniki.
Thank you very much. I'm Aris Christou, University of Maryland in USA. I'm very happy to chair the first session and very happy to be here in person after 2 years of attending virtual conferences, to have the opportunity to be present in person and to talk with many of you and to interact with colleagues and fellow scientists. We're very fortunate this morning to start off Workshop 1 with our keynote speaker, who's Professor Andreas Offenheiser, Jülich, Germany. Professor Offenheiser will speak to us on engineering the neuroelectronic interface with nanoscale tools.
Yeah, thank you very much, and I'm also very happy that I can be here in person after 2 years of let's say, virtual conferences. I hate these virtual conferences, and I'm glad that you could organize a real conference. Thank you very much for inviting me, and I'm also glad that I will start this series here with my presentation, which is on, let's say, the interface between nano tools and live cells. So I guess it's a nanomedicine, nano or bioelectronics session. So as most of you know, our brain consists of neuronal cells, and these neuronal cells are connected through synaptic connections to each other. They transmit signals, and the synaptic transmission is one of the major part of this, let's say, neuronal signal processing. This involves, on the one side, that the neurons produce a so-called action potential. So this is the electrical signal which a neuron can produce, and which sends it over the axon to the synaptic cleft, where it then produces a so-called postsynaptic potentiation or postsynaptic signal. And this is what happens in our brain every second, so that postsynaptic signals are produced, and at a certain point they lead to action potentials. How to study neuronal signal processing, I mean, we cannot go to the humans. There are not so many people available which are contributing their brain. So there are many model systems around, and they start from, let's say, worms, to flies, to fish, to mouse, and to rodents. But on the other side, there are also lots of model. Does not work. There are also lots of model systems which are working in situ, so kind of in vitro model systems. And for all of this, one needs to find tools to measure the electrical signals. So, and one of the, of course, the gold standard is the so-called patch clamp technique. And the patch clamp technique, for this, you use a glass pipette which you bring to the cell or to the muscle, and then you open the cell membrane, and then you get direct connection to the cell interior. And by this way, you can measure with the highest standard, with the best signal to noise level, you can measure the signals from the cell. However, this is invasive, and it works typically only for a couple of hours, then the cell is usually dead. So one is looking for other alternatives. And one alternative is a so-called microelectrode array. And in this case, one measures from the outside. So this is how the, let's say, microelectrode array is fabricated. You have these metal leads which go into the center of the microelectrode array. Activation, and there's a one spot opening, and typically you record from this spot here, you record the activity of neurons. So these are nowadays kind of standard. So on the one side, you have the patch clamp electrode, which is invasive, which is very powerful, but you can handle typically only a couple of patch clamp electrodes at the same time over a couple of hours. On the other side, you have microelectrode arrays where you can record from the outside of the cell for a long term, let's say from many neurons, which allows you to analyze neuronal activity of networks. However, there's the so-called unsolved cell electrode coupling challenge. And this comes from the fact that when a cell sits on an extracellular electrode, there's always a gap in between because the cell needs to adhere to this substrate. And this leads to an electrical circuit model, which indicates already here one of the main problems. This is the so-called seal resistance. And this seal resistance is formed by the cleft between the cell membrane and the electrode. And I come to this in more detail. So to simplify it, the electrical circuit model looks like you have the electrode indicated with a resistor capacitor. You have the cell membrane in contact with the electrode, also resistor capacitor, and this cleft here forms an electrolyte filled conductor. So this can be modeled by a resistance. And now the size of this resistance determines what you measure, more or less. So if this resistance is high, the signal will be high. If this resistance is low, the signal will be low. And as a consequence, with classical microelectrodes, you record only a very small fraction of the action potential of a cell. So typically 1 or 2% maybe of the action potential. And this will not allow you to measure this so-called postsynaptic potentiation, which I mentioned at the beginning, the signals transmitted between the synapses. So to better know what or how large this gap is, one needs tools to characterize this interface. So how large is this gap? And one way, of course, is as usually always electron microscopy. So in electron microscopy, for instance, you make a cross section, or first of all you embed your cell in a resin on the substrate. Then you make cross section of this situation, and then you analyze in detail the cleft between the cell membrane and the electrode. And when we do this, we find distances typically in the range of 50 to 150 nanometers. So a cell is not approaching an electrode closer than around about 100 nanometers. Of course, you can imagine that such a method takes time. I mean, this preparation for this cell took about 1 week time. And this is, of course, very time-consuming. It's very expensive. And we were looking for alternative ways. So one way is to use so-called focused ion beam cross-sectioning. So focused ion beam cross-sectioning is used typically in semiconductor technology to characterize materials, to make cross-sections and then look by electron microscopy and characterize materials. And Francesca Santoro, which did a PhD in our institute and is now back as a professor in our institute, she developed a method where she was, instead of this classical, let's say, a critical point drying, she was using a resin embedding, or developing a resin embedding. In this case, the cell was embedded in the resin, and then the resin was washed away in a very quick wash, and then one could do again this cross-sectioning, in this case by focused ion beam sectioning. And this gives very, very nice and very detailed views of the cell on the one side, especially when you do staining. So you can do heavy metal staining of the cell membrane, and this gives very details. You can see here cell membranes, you can see the nucleus, you can see vacuoles inside of the cell, and on the other side you see in detail the contact of the cell to the substrate. And you see the cleft, yeah, and you see the distance between the cell membrane and the electrode. However, again, this is a very time-consuming process. I mean, it takes a couple of days, especially when you do osmium staining. You have to take care on safety issues. And focused ion beam is something which has a $1 million price tag as a machine. So it's also not something you can just buy and so on. So we were looking for other possibilities. And one way to analyze the interface between a metal and, let's say, a cell is the so-called surface plasmon resonance microscopy. So in surface plasmon resonance, you shine light under a certain angle on a metal surface, and this causes evanescent waves, and this evanescent wave is very sensitive to what happens on top of this metal layer. And by this way, you can study in situ the interface between the cell membrane and the electrode. We have, let's say, used on the one side this live imaging surface plasmon resonance microscopy. As you can see here, now you see really in situ. So the cell is still alive when you do these experiments. You can see in situ how far the cell membrane is from the electrode. And to get more details, one can do a so-called focused surface plasmon resonance microscopy. In this case, one focuses only on one spot and analyzes always the reflectance curves and can model for every spot a reflectance curve. And by this way, you get a very detailed information on the distance between the cell membrane and the electrode. On the one side, you get information about the refractive index, indices, and by this way, you learn also a lot on how the cell membrane is behaving. And doing this, one can really do a kind of a three-dimensional plot of the let's say, interface between the cell membrane and the electrode. Here, an example for a neuron. So, how far is a neuron away from the electrode? And you can see now here's the distance profile, and you see some parts are very close in the range of 40 to 50 nanometers. Some parts are rather in the 100 nanometer range. As I mentioned before, what we have seen with electron microscopy. And we did a comparative study and found that this, let's say, surface plasmon resonance microscopy gives very similar results than focused ion beam measurements. So coming back, so what can we now do to improve the recording? So I mentioned typical microelectrode arrays. You get very small signals. You are not able to do get postsynaptic potentiations. So how to improve? And here the idea is to go 3D. Yeah? So to go to use rather 3D structures than a planar surface. Because the idea is a cell likes not to sit on a glass substrate or on a very slippery, very smooth substrate. A cell likes to sit on a rather rough substrate. And so we use both. We use on the one side so-called nano cavities, and on the other side nano mushrooms or nano straws. So for nano cavities, here the idea is so we have an aperture, so a small opening where the cell sits. So you can think about this is similar to what a patch clamp electrode has as an opening. And then we have the electrode, and above this nano electrode is a nano cavity. And this nano cavity is mainly for the purpose of, let's say, increasing the surface. Why do we want to increase the surface of the electrode? Because the impedance goes down as a consequence of large area. And when the impedance goes down, the noise goes also down. So that means we get very low noise level for the electrodes, and we can record with this method very high signal-to-noise ratio signals. And here is how we do it. So we add, during the preparation, we add a chromium layer, and this chromium layer is then later etched away, and this gives this kind of openings. You see these bright spots. These are the under-etched nanocavities, while here is the electrode opening. And this gives very nice signals. So for instance, here we have measured from cardiac myocytes signals in the range of millivolts instead of let's say 100 microvolts. And when we do cross-sectioning with the focused ion beam, we also see that the cell membrane goes into this nanocavity and closes this nanocavity gap. To better understand, especially how is the optimal geometry for this recording method, we did measurement with, let's say, a coupling between patch clamp electrode on the one side and microelectrode array on the other side. This is a very difficult measurement. I can tell you, not a lot of people can do this. Not a lot of students are able to do this. Very time-consuming, very delicate. But what you can do now is you can do simultaneous measurements, and by this simultaneous measurement you can evaluate, for instance, the seal resistance, you can get details about the coupling and so on. And doing this, we found out, for instance, that it seems that a kind of an 8 micrometer opening is the optimal configuration for the best recording. And this allows us then also to do recordings from neurons with a very large signal, so in the range of 400, 500 microvolts. This is very large. I mean, typical microelectrode array recordings are in 100 microvolt range. And again, also with neurons, we find that the 8 micrometer opening seems to be the optimal opening for such a configuration. How to improve more? So there are quite a number of approaches, and I think we will hear in this meeting another approach as well for, let's say, so-called in-cell recordings. You can do penetration from the outside. You can build 3D nanostructures which penetrate the cell membrane. But most of these approaches require so-called electroporation or optoporation. And we were looking for an approach which does not need this, let's say, poration, because this somehow changes the cell, and you never know if the cell is the same after poration than before. So we were following an approach which was developed by Nick Melosh in Stanford. So he developed this so-called nanostraw, and he used the nanostraw for delivery into cells. And we combined these nanostraws with our microelectrode arrays, especially this nanocavity microelectrode arrays. And these were formed by, let's say, an ALD process on the nanocavity electrodes, and we could form these nanostraws which have a conical shape and which have, you can see here, about 140 to 160 nanometer diameter at the base, and about 200 at the opening. We studied how these nanostraws are interacting with the cells, and what you see here is that the nanostraw really go into the cell. At least it looks like. At least from the electron microscopy images, we have the impression that the nanostraws are really inserted into the cell. And when you look a little bit more in detail, so you see here the cell nucleus. So the cell nucleus is not penetrated, but the cell membrane seems to be penetrated. So this is what other people also found, and it confirms that the cell nucleus has a different properties than the cell membrane. We then did again recordings. So here you see recordings with these nanoelectrodes. So with these nanostraw, nanocavity electrodes. These recordings are without electroporation. So these are, let's say, kind of the cell sits onto the electrode. Obviously, the nanostraw penetrates by itself into the cell, and we get quite large signals. So up to several millivolt signal size. Typical, let's say, average signal is maybe 800 to 900 microvolts. But what was also very interesting is that these high signals are stable for a long time. You see here, after 18 days in vitro, so around about 2.5 weeks culture, after 3 weeks culture, and so on. And we can record this high signals for a long time from the neurons, as long as the neurons are alive. The recordings we did, so here are a summary of many spikes, here a typical recording. The recording looks a little bit like an intracellular recording. I don't want to claim it is an intracellular recording. It looks like an intracellular recording. So it means that we are in between the typical extracellular recording and the classical patch clamp recording, I would say. Here's a kind of an analysis of the signals we recorded. So we have quite a high portion in the range of millivolts recordings. But we have also many different shapes. We are still in the phase of finding out why the shapes are different, why we don't get all of this typically in-cell recordings. And we have looked into the distribution. So the most signals, we have this positive phase signals. For the experts, this means probably very close to an in-cell recording. What is, I mentioned already that this is stable for many days because it was not due to an electro or optoporation or any chemical means. What we then also did was we looked into, again with simultaneous on-chip patch clamp experiments, we looked how does the intracellular signal looks in comparison to the extracellular signal. And what you see here, so the difference here, the intracellular signal is still a little bit longer, the extracellular signal is a little bit shorter, which indicates it's not a complete in-cell recording, it's probably something in between, so it comes from the membrane probably. So if we compare the blue signal here, so this is from the microelectrode array, to the black signals, this is from the patch clamp electrode array, they don't match perfectly in detail. But what was very interesting for us, it was that we found not only action potentials, we also found postsynaptic potentiations. So this is the first time that people report postsynaptic potentiation without any poration, electroporation, So this was just by chance. These signals were recorded, and you see here the postsynaptic potentiation measured by the patch clamp electrode, and here you see the postsynaptic potentiation measured by the nanocavity nanostraw electrode. And and they now match quite nicely to the signals we expected. So in summary, here with this nanostraw, nanocavity microelectrode arrays, we are able to record very large signals spontaneously from neurons, which resemble probably a kind of an in-cell signal. And we are able to record also postsynaptic signals from the cells. And this allows us, of course, now to look in more details into the neuronal communication on a postsynaptic level. So rather on a synaptic level than on a action potential level. So in summary, I talked today about, first I mentioned that it is important to understand the cell-device interface, and for this we use, on the one side, we use a method of resin embedding and focused ion beam sectioning, but also the setup of a surface plasmon resonance microscope, which allows in situ live study of a cell, and by this you can also study the dynamics of cell adhesion on an electrode in detail. I mentioned that to optimize a signal or to get better recordings and to have also signals from the, let's say, postsynaptic potentiation signals, it is necessary to think about tools, nanostructures, which allow, on the one side, to improve the seal resistance, but to get really also subthreshold signals from neurons. And we believe that these nanostraws, in combination with a nanocavity electrode array, is a very good tool for this. With this, I want to thank the people which have done this work, and I like to thank you for your attention. Thank you.
Thank you very much. We have time for a few questions.
Firstly, thank you very much for your very interesting presentation. I would like to ask a clarification more than it's a question. Regarding the geometry of the substrate that you've been using, it's like the nanostraw, right? So you've mentioned that also the geometry has an effect on the amplification of the signal, or probably will have an effect on improvement of the intracellular recordings. Also because recently we have seen a similar presentation that almost this kind of similar geometry that is the conical shape. So I'd like to understand to what extent or what kind of geometries that one could use to have an improvement in such a recording. Thank you.
Yeah, let's say, I mean, if you want to use nano tools from the substrate, I think this kind of nano straws, nano cones, whatever, are the right way to go. And I think there is a kind of a rule of thumb that these nanostructures should have an aspect ratio higher than 14 to 15. So obviously, you need to have a very sharp, either needle or nanocone, nanostraw. I cannot tell what is better. At least for us, it worked very nicely, especially it worked spontaneously. So we did not have to force the cells to break the cell membrane. And I think this is, I mean, if you think about what electroporation does to a cell, you don't know if it is still in the same shape. So I think, at least I believe, one should try to avoid electroporation to get this good contact.
Any other questions? Well, I had one. If you could clarify whether the focused ion beam milling does any damage to the cells. It's an energetic process. So.
Definitely. I would say, of course, you cut through material. The material, it's an organic material, and you bombard it with heavy ions. So I'm pretty sure that you damage the first angstroms nanometer of the cross section. But with this focused ion beam milling, you typically look. I mean, we use typically scanning electron microscopy. So this is not so accurate. We are now trying to get into cryo mode. So doing cryofixation and cryo milling. I'm not sure if this is really the better choice, but definitely, I mean, this is not a perfect process, but of course,
okay.
It's only a limited damage, I would say.
Okay, let's thank Professor. Okay, our second talk today is by Dr. Connolly from GPS in Paris. And is he here? Yes. And
Yes.
he will talk to us about simulating experimental techniques, Kelvin probe force microscopy.
Okay, shall I share my screen now?
Yes, you can share
Can you
it.
hear me? Okay. Okay, can you see me? Can you see the slides?
Yes.
Okay, so good morning, everybody. All I can see is my slides, so I can't see the audience. So thank you for having me at this meeting, and I'm glad to participate in particular because there's a partnership with a journal that we have here in France, which is EPJPV. So on to the talk. So I'll talk to you about simulating experimental techniques. And this work is in partnership with partners in Paris first, and with Veselin Donchev in Bulgaria and Ahmed Nejim of Silvaco in the UK. And I'm financed by this project Bob Tandem, of which you can see the logo here in the middle. And the partner institutions are Centrale Supélec, JIP, CNRS, Sofia University, and IPVF. So moving on, a quick summary. First, we'll introduce what Kelvin probe force microscopy is, and then we'll have a little look at analytical and numerical methods. And then I'll take you through simulating experiment in detail. A word with respect to the abstract. I was intending to include more modeling of experimental data. This has not been possible for a range of reasons. So what you'll see is mostly a description of how the model works in some detail. So first, what is Kelvin probe force microscopy? It's a method of measuring a surface voltage, which can be as a function of incident photon energy, or it can be in the dark. The difference between the dark and light is the surface photovoltage, which yields much information on the band structure of photovoltaic devices, in particular solar cells, which is my focus. It also allows the study of semiconductor materials and surface and interfaces, in particular optoelectronic devices. It's contactless, non-destructive, and there's no sample preparation or junction fabrication required. All you need is a contact on the back, and the probe is not in contact with the surface that's being studied. From this technique, with quite a lot of analysis, which is difficult, you can extract information on the type of doping. You can also extract band-to-band transitions via surface photovoltage spectroscopy. You can also evaluate diffusion minority carrier lifetimes, and you can evaluate the open circuit voltage of a solar cell. And so the challenge is, because it's a surface technique, it's dominated by surface defect. And the solution to this is modeling. So how does the technique actually work? You have a atomic probe. So it's derived from atomic probe microscopy. I should have started by mentioning that. So you have an atomic probe which you scan over a surface, and the atomic probe is controlled by crystals which allow a very, very sensitive position control. There's two modes. One is the amplitude modulation, so it's the amplitude of the signal as a function of the frequency applied to the bias. The other one is frequency modulation. I won't go into detail on this because this is more of the specialization of my colleague Jose Alvarez. This talk is mostly about modeling. A brief sketch of the technique looks like under light from Clément Marchal's PhD thesis. Moving on to the equipment, Kelvin force probe microscope looks a bit like this. And so we apply a bias to the Kelvin probe, and we minimize a field between the sample and the probe, which is sensed the force on the probe, which is sensed by a feedback mechanism. We can illuminate with lamps or monochromators, and we can look at the difference between light and dark. And this gives us SPV, surface photovoltage spectroscopy. Now, what actually happens, and how does this look like from the sample point of view? Here on the left, you see a semiconductor material with defect states at the surface, such that there's a space charge region in front. In this situation, first of all, we can measure the work function of this material simply by applying a bias to our probe. And when we have the zero force or zero field condition, we compare that bias with the known work function for KPFM tip, and this allows us to deduce the work function of the material. When we illuminate it, we get a quasi-Fermi level thing, which changes the conduction and valence position at the surface, and, well, in particular the Fermi level, and therefore changes the work function. This is why we get a difference between the light and dark, which allows us to define the surface photovoltage as sketched here. In the dark, the work function is affected by the surface charges, as we've just seen, and we also need to know the work function of our Kelvin probe. If we look at the light, however, it's slightly different, because the light, the SEV is independent of the atomic probe function, because it's a difference. So the work function of the probe is eliminated. It's a point worth remembering. It's easier in some senses to measure SV than it is the dark signal. Now, a sketch of analytical models. I won't go into this in detail, although there's quite an interesting talk to be given on this subject alone. But we can, this is my colleague Jean-Paul Pieder of the CNRS, who's been looking at this and has developed an analytical modeling of band bending near the surface, which is implemented in MATLAB. So it's numerical to some extent still. And the value of analytical models is that it allows us a deeper physical understanding of problems that we look at, as opposed to numerical models where the physics of the system is slightly further removed. So we've compared the band bending of a bulk silicon material and without acceptor and donor defects. And we've compared this with the numerical model, which is using Silvaco software, where the numerical model allows us, within reason, arbitrary defect distributions and arbitrary geometry of our sample. In practice, of course, we have convergence issues and so on and so forth, which many of you will be familiar with. The object that we're studying is bulk silicon, and in the analytical model, we have a 2D surface state distribution, so that's square centimeter. The 3D model uses bulk. We've studied this, and this is no difference to this SV measured or the band bending. The extent of the volume versus surface is actually the same. As long as the total density of charge, the number of charges is. So moving on to an analytical and numerical comparison. This is very recent work, so it's just a start. At the top, you see the SPV as a function of light intensity, where here the light intensity is described by the excess minority carrier concentration. It's at delta N, because this is p-type silicon they're looking at. So this is the surface to voltage as a function of illumination for a range of acceptor and donor defect densities, where the distributions are, well, I won't go into detail on the distributions, just to say that they're Gaussian distributions, which are close to the conduction and close to the valence band, respectively. On the left, we see this calculation for capture cross sections, which are equal for electrons and holes. And we've been looking at having asymmetric capture cross sections on the right, which is actually more physically exact, where you have a factor of 100 between electron and hole capture cross sections in donor and acceptor defect distributions, respectively. On the bottom, you see the same calculation, but this time in terms of incident flux directly, which is more representative of what of an experimental measurement. This gives it makes the two distributions slightly difficult to compare exactly. So all I'll say at this point is that we have qualitative agreement. We have a SPV versus flux measurement, which is similar between analytical models, which give us understanding, and numerical models, which are more exact. So, and there's plenty of future work in here, which will be the publication we are planning as a result of this presentation at Nanotexnology. So moving on to the main body of this presentation, which is, after all, how to model experiments. So a few words on the simulation strategy. You might think when we want to measure a Kelvin probe experiment that one should simulate the motion of the tip. However, this is extremely computationally intensive, and it is beyond the capability of standard numerical software. So this would require a fair amount of development. So what we've done is to solve a static case where instead of solving precisely the motion of the tip and adjusting the bias until the force is null, what we do instead is we solve the problem to achieve a zero field between the tip and the sample. This, I call it a static work function solution. And to simulate the experiment, we sequentially move the probe across the surface of the sample, just as the experiment would. And the method is to use commercial numerical software by Silvaco as a computational engine. And I've written a software pilot or driver, which sequentially writes the Silvaco input script, calls the program, does data treatment, and so on and so forth. So below, you have a brief, well, it's not that brief, flow chart of the program, which is the CalScan KPFM model. And it reads, saves, modifies material structures, models, and all the rest of it. And is quite long, and there's there's many different parts to this piece of software. So moving on to first a reminder, the Kelvin probe method, which is as sketched in this figure here. And what we do is we see in the first figure A the situation where we have sample and tip that are far apart. As we're bringing them together, the difference in work functions generates charges, negative and positive charges between the two to balance difference in work functions. What we do is we apply this DC voltage between the tip and the sample, and as you see here, we eliminate charges and we eliminate the field between them. And here is an example, as just to show you in practice what we're talking about. On the left is a sample, and on the right is a zoom on the actual tip, where you can see the tip being made of metal needs very few hit points, but there's greater resolution in the volume of the material. So moving on to the solution methods, what we do, there's 4 examples here because there's actually a number of different ways one can minimize the field. One can minimize the net field over the entire surface, which gives you a reflection of the shape of the tip and is actually preferable. However, it's also very slow. So not to spend much time on this because time is passing quickly. I better speed up a bit. What we do is we look at one spot between the probe and the device, which has the disadvantage of not taking account of the probe dimension, which is a shortcoming, but we'll bear with that for the moment. So a brief demonstration of the project and of how it runs. And since this is a large number of screen captures, I won't spend too much time on this. But first, you see the interface of the program here, CalScan, and the option 1 is to read a sample. So this is all text-based, good old-fashioned programming without the use of a mouse. We choose a sample. This is a sample modification menu where we can modify all aspects of the material, that is to say the number of layers, the doping, the defect densities, etc. donor and the capture cross sections, etc., etc. We also define the probe here. So we define the probe dimensions and work function. Next point is the sample file format. Okay, this is a minor detail. The sample file contains all properties of the simulation. It includes the scanning, it includes the size of the book, and so on and so forth. The sample file is actually a Silvaco input file. And so it can be read directly by Silvaco, and it's read by CalScan in order to reread all the parameters that have been put into it, which is computationally is a slightly tricky thing, because reading and writing sample files is actually difficult. There's lots of interesting things to talk about that, but this is not the time or place for that. So this is a sample with many layers, 20 layers, but we won't dwell on that too much. We can change the doping levels. We can see the doping levels, which here the resolution is a bit low, but these are the defect distributions in our device. Then we can change the KPFM probe. I'm accelerating here a little bit, but this is just to give you a brief appreciation of the various parameters that you can modify. So tip position, the gap between the probe and the sample, probe length, width, work function, and material, of course. So the first thing to do is a simple static solution. So this is just an appreciation of the structure. So this is a multi-layer structure here on the right. This is with acceptor defect distributions in this case, and this is just to see what we have and what it looks like. And in this case, I'm plotting the electric field as a function of position across the cross-section of this device. Only plot, we can choose many different quantities to display. So we have the band structure, we have the quasi-Fermi level, say many, which I will go into. And the prime function, as we've already seen earlier when I talked about the solution, is the contact potential, which is via option 6 and 7. There's a range of methods, as I mentioned earlier, and we prefer the spot method, which is quick, even though the minimization method over the whole volume is in fact more exact and takes the probe dimensions into account. Okay, so this is not of great importance. What's most interesting is the contact potential scans, because this is what is mimicking or simulating the KPFM experiment. So what we can do is we set the position and the resolution, and we obtain things like profiles such as this. So on the left, you see a VCPD, that's the contact potential scan, over a PN junction. And the doping is shown here on the right. Then we have implemented parameter scans, where we can scan not only the position, but we can also scan defect donor density, acceptor density. Actually, from 1 to 3 parameters can be scanned at one time, which allows us to do 1, 2, or 3-dimensional surfaces for solution. This is a very quick way of identifying solutions. If, for example, you're thinking of where do I have specific contact potential as a function of doping density and surface defect densities. And we'll look at an example of this in a minute. The time is running low. So So this is examples of scans for a number of parameters. And forgive me for scanning through these screens a little bit quickly, but these are all just specific examples of how this model works. And here we'll do an example of a dimensional profile. So this screen shows the parameters that are being picked. And this shows rapidly the two-dimensional CPD plot as a function of effector defect peak density and donor defect peak density. So the thing to remember from all this is that this is a tool that allows exploration of a large number of parameters in a flexible number of ways, and thereby helps to simulate the experiment and the KPFM experiment and understand what's happening. Another example, because what we've been looking at until now has just been CPD. So a quick example of surface photovoltage. Here we have a PN junction. We have the surface defect donor distribution here in figure 2. And here we see a cut of the band structure. And what we see is that on the P side, P silicon here, since we've put donor defects at the surface, we have a surface depletion layer. And a surface depletion layer, if you think back to the beginning of this talk, the depletion layer is where you will have a quasi-Fermi level splitting, and you will have an SPV signal. If you have a heavily doped surface, you see no SPV, simply because the Fermi level does not shift under moderate illumination. If you go to very high illumination, you will see an SPV, but this is why, figure 4, you can see this shows the CPD sense in the dark and in the light, and in the red it shows the, in the blue it shows the SPV. And we see an SPV on the side where we have a depletion layer. And we see the opposite behavior if we add acceptor defects. So, concluding remarks. So the focus of this presentation is not completely in line with the abstract, where I was hoping to talk more of experimental data, but we have had some issues with some measurements. And so I focused instead on describing the KPFM modeling techniques and the design of a user-friendly numerical modeling interface. The next steps will be to refine descriptions in KPFM tip size in particular, which I've mentioned a few times, analyze new materials, and especially to plan a publication in EPJPV, which is a partner of Nanotexnology. Final important point, support for this work is from Solar Eranet, H2020 program, project Bob Tandem, which is finishing at the end of August, of which I'm the coordinator. And so thank you for your attention. And that's the end.
Okay, thank you very much. We have time for a couple of questions. Yes.
Hi.
Hello.
So at any moment you didn't mention let's say, how much the tip is embedded into this modeling of yours. So only in this outlook you said you want to add additional parameters on your tip. However, if you do KPFM, it's pretty much tip dependent. It's pretty much centered on the tip, right? So I just wanted to understand better with respect to the tip.
Well, let's go back to here. The tip that we have is rectangular and is usually about 10 nanometers across. So the rectangular aspect is already questionable. One could quite properly say, oh, you should have a rounded tip to reflect reality. Do you agree? However, that's the extent to which the tip is implemented model. So you can define the width, the material, the work function, and the geometry of the tip, but only as a rectangle at the moment. And even if that's not perfect, it's a fair approximation to some way.
But then I can give you a simple example. You have your tip, and you just put one small grain on top of it. All your results will be different, won't they? So let's say the electric field...
Okay. Let me ask the speaker, can you answer that question quickly so we could move on?
A grain on top of the tip would make no difference. If there was a grain between the tip and the surface, yes, it would make a difference. But a grain is not a problem with the tip, it's a problem with the surface. So what you're talking about now is impurities between the surface and the KPFM tip, which is a different issue. What we do is KPFM measurements in the air. So yes, there are artifacts such as dust and so on and so forth. I have not gone into that, but this is true. That's a good point.
Okay, thank you very much. Please follow up by communicating, with email or other means for further questions on this. Okay. Our next speaker will be on adhesion lithography for nanogap electronics by Dr. Faber from Saudi Arabia, King Abdullah University. And this is an in-person presentation.
All right, good afternoon, everyone. Thank you for the introduction. My name is Henrik Faber. I'm working in the LAMA group of Professor Thomas Antopoulos at KAUST University in Saudi Arabia. And I'm delighted that the organizing committee is giving me the chance to present a couple of our recent research work today. Specifically, I'll be talking about adhesion lithography as a fabrication tool for nanoelectronics. And I want to first explain what the technique is, how it works, and what you can do with it. And then transition over into 3 different studies that we recently did which deal with high-frequency electronics. I want to start off with a very simple premise that essentially all electronic devices make use of conducting electrodes that at some point connect that with some active material, let's say a semiconductor that is used for sensing purposes. And pretty much in all cases, you benefit by reducing the gap size between the electrodes. Right? Normally you get an improve in operational speed, maybe reduce the operation voltages. So in any case, it is beneficial for you if you have a situation like this, where you have one metal electrode on one side, one on the other, and a separation of only a few nanometers in between. Now the question is, in a regular research lab, what kind of techniques are available to you to create this kind of structure? You could use something like e-beam lithography. There are scanning probe techniques that can do it. You may be able to do a break junction. But all those techniques come with certain downsides. Typically, they're either expensive, they're rather slow, they don't really work well with large areas. And oftentimes, they will have difficulties creating a situation where you don't have the same material on either side of the gap, like is shown in this case, where you have 2 different metals. So we're using a technique called adhesion lithography. That is, as you'll see, rather simple, but it still allows you to do these kind of, we call them nanogap electrodes, in a fairly simple and cost-effective way on large area. Right, so let me run you through a typical the process steps. We start off with a substrate, and normally we're using, as you can see, sort of 4-inch wafer sizes, so already fairly large areas in that respect. You start off by depositing a first metal everywhere onto the substrate, and then you bring it into shape, you pattern it. Typically, we use photolithography here. And we're using resolutions that are very relaxed, so like micron to millimeter size patterns that we introduce. And then the most important step is the following step, where we do a surface treatment of this patterned electrodes. Right? So we're applying a self-assembled monolayer, or SAM for short, which is made up of a short organic molecule, typically about 3 nanometer in length. And these molecules are chosen in a way that they specifically interact with the patterned first metal, but they won't bind to the substrate itself. Right? So in the case of the example that I'm showing here, we're using aluminium as a first metal, and we're choosing a molecule, ODPA, which has a phosphonic head group, which likes to bind to the native alumina, which is forming on the aluminum, but not to the substrate material. What those SAMs are doing now is they change the surface properties of the first metal. They make it very hydrophobic, as you can see in the contact angle picture. And essentially, they reduce the adhesion of anything that comes on top of it. That's where the name adhesion lithography comes from. Those SAM molecules are, as I said, specifically chosen with a metal that you want to pair it with. If, for example, you wanted to start with gold as your first metal, you wouldn't use a phosphonic acid-based molecule, but instead something like a tile group, like you can see on the right-hand side. Now, if you go on and you deposit a second metal everywhere on top of the substrate, the second metal will have two different regions and spaces. Either it's sitting directly on top of the substrate, where the adhesion to the substrate is just normal, so there's no problem, or it's sitting on top of the first metal, which is treated with a SAM, where the adhesion is very greatly reduced. So now what you can do is you can apply a piece of tape or a kind of adhesive glue, and then remove it. And as a consequence, all the areas that were initially overlapping the first metal will be taken away. And if you do it right, you end up with a situation where you have metal 1 on one side, metal 2 on the other side, and the nanometer size gap right in the middle. Right? The good thing about this technique is that it's essentially flexible in all of these process steps. You can choose different substrate materials. You can do glass, flexible substrates are possible. The metal combinations really only depend on if you can find a SAM that works for the surface treatment. And you're free to choose either symmetrical electrodes, so the same metal on either side, or asymmetrical electrodes, like in the example picture here. A couple of other examples. You're really completely free in the way that you pattern your first metal. And as I said, you can do fairly relaxed resolutions. You can also use different techniques. Initially, we do it at shadow masking, or we tried out laser ablation in these examples down here. And the beneficial thing is really that the resolution of your patterning is decoupled from the size of the nanogap that is created as a result of this peeling, right? So this is very beneficial for your process. And as you can see, you can do this on different substrates. You can make flexible devices, for example, on PET. I want to say a few words about the nanogap size. If you look closely in those pictures here, you see that the gap size is following the contours of the grains of the metals. So by changing those parameters, the different evaporation rates, for example, you can fine-tune the edge of your gap. And then, obviously, because this is at the moment, it's a manual peel-off process, so it will depend on the operator. If you do it quickly, if you do it very gently, you'll get slightly different results. As you can see in the example here as well, it may matter in which direction you take the peel-off, where you can have a size variation of about 20 nanometer between either case, essentially. One thing to note as well, which is maybe the one main drawback here, is the technique is good to give you gap sizes like this in the range of 20 nanometers. It is not very good if you want to precisely dial in, let's say, a range of gap sizes of 20, 50, and 100 nanometer. So this is not what this is good for. All right, with the ability to make those gaps, you can then factor into different semiconductors, different arrangements, and you can make different kind of electronic devices. Here are a couple of examples that we've done to incorporate these into transistor devices, make memories, make devices that can either sense light or emit light. And there are different other things we're looking into at the moment, and if you have other ideas what we could use them for, please come and talk to us. We're always open for that. The main applications I want to focus on in the rest of the talk, you can see on the top right, is to make rectifying Schottky type of diodes for the use in high-speed electronics. And as a quick intro, why those kind of diodes might be useful, I think we all have heard the term Internet of Things. Our smart devices are constantly connected to the internet and to each other. And as part of this infrastructure, it is envisioned that we'll also have lots of small sensors that are distributed essentially in the world around us. And all of these autonomous small sensor nodes need to have some sort of power source. Batteries are not really applicable in this case. So you need to find some way to power them. Something like solar energy would be one option, and another option would be to take and harvest energy from RF signals that surround us essentially constantly, from sources such as Wi-Fi signals, cellular, or Bluetooth, right? So this is all stuff that is operating in the gigahertz range. So a very simplified schematic of how we could use this to capture energy is you can see in the top right, where you have an antenna that can pick up the signal in the first place, and then a rectifier unit that is producing a DC output voltage that can then be used to power your sensor node, right? In the very simple case here, you can have one diode embedded in a half-wave rectifier circuit that is taking the signal and rectifying it, giving you an output voltage. And the figure of merit to judge these is called the cutoff frequency, giving you a measure of how fast your device can operate. And it's, for the most part, determined by two parameters called the series resistance and the junction capacitance. And you want both of these to be as small as possible in order to give you the highest speed that you can harvest. All right, let me go to the first study that I want to show to you today, where we use nanogap electrodes that are comprised of two different metals. We have aluminum on one side, and we have largely gold on the other side. We're using a small adhesion layer that makes the gold stick better to the substrate, but it's mostly gold that acts as the active element. And you can see we often have this structure where we have one circular electrode that is completely embedded with the second metal electrode on the outside, and the nanogap is running along all the circumference of the inner electrode. Right? So in this example, we pair the aluminum and gold nanogap up with a solution processed N-type oxide semiconductor, zinc oxide in this case, to make a Schottky kind of diode. One thing to note here is if you paid attention after the peeling off step, this SAM molecule is still sitting on top of the first metal, and those are typically insulating molecules. So before we apply any semiconductor, we need to make sure that we remove that SAM. And luckily, this is easily done either with a UV ozone treatment or some short plasma treatment. And then your device is ready for the, in this case, a spin coating, annealing of the semiconductor, and you're ready for your device. The other question, or one other question that we often get is, for this kind of nanogaps, are we actually able to fill the semiconductor into the gap? Which is why I'm showing the picture here. The elemental analysis on the bottom right is showing that the zinc coming from the zinc oxide, you can find it on top of either side of the electrode, but also very much in the center of the gap. So obviously, this kind of TM analysis is quite costly, so we can't do this in any case. Sometimes we see the fillings better, sometimes we don't, but in general, it's possible to fill the gap. Right, let's look at the electrical characteristics of this kind of diode. First, the static IV results, and as you can see, we indeed have a functioning diode, so we have very low currents in the reverse bias, where it shoots up over several orders of magnitudes at the forward bias. So that's as we would expect. And then we often, just as a sort of like sanity check, we try to vary some of the input parameters. So in this case, you can think of the diameter of the circular electrode in the middle. As we scale this up, we see that we get a higher current as we would expect because we have a larger circumference, essentially. Something I'm not going to talk much about here, but I'll pick it up later in another study. When you use solution processing to put down your semiconductor, you get all the benefits that come with it. So you have the easy option to include something like a doping in the process to tune the parameters of your devices. Okay, so we made sure that we have a diode. The question is, how fast do they operate? I was mentioning cutoff frequency as the figure of merit, and there are typically two ways how people can measure it. One of them is called the intrinsic cutoff frequency, where you just send the signal and you measure whatever is reflected back from it. And this technique gives you what is called the intrinsic cutoff frequency, which is sort of the upper boundary of what the device should be capable of. It's neglecting a couple of losses that happen in a real application. So a better way to do it is to measure the extrinsic cutoff frequency. So the way this is done is shown schematically up here. Essentially, you have a very specialized function generator that can generate gigahertz AC signals. You send it to your device. Your diode is causing for the rectification, and the DC output voltage is then measured across a load resistor. Right? What you would expect is that as you increase the frequency, the output voltage that you see eventually starts to decline because the diode cannot follow the high frequency anymore. Right? If we look at the results, this is exactly what we see here. So we have fairly steady output voltage in the beginning, and then slowly we decline. And the cutoff frequency is then defined as the voltage where the initial level drops to, 1 over square root of 2. Right? So the good thing here is we do indeed reach the gigahertz frequency range for our cutoff frequency, which is the target that I was mentioning earlier for signals such as Bluetooth or cellular networks. Here as well, it's always good to verify that what you measure is making sense. So as you imagine, if you change the input power that you send to your device, if you increase this, you would expect that also the output that you get is increasing. And this is shown in here. If you go from the blue curve up to here, the input power is increased, and also the output signal is increased as a result. The other thing is that this device here is a fairly large diameter diode. If we shrink this down in size, there are two things that are happening. First of all, you see the level of the output voltage is declining because our device is now smaller. It can't give you such high voltage anymore. The other thing is that if we shrink the diode size, we're also shrinking those parameters that I was mentioning earlier, series resistance and the capacitance junction capacitance, which in turn gives us a little bit of a boost in the cutoff frequency that we measure. So smaller devices give you a higher speed. Ultimately here we have highest values of around 7 gigahertz, which if we put it on this map, we see there's a mix of intrinsic and extrinsic cutoff frequency that were measured for different materials over time.
Sorry for the wait.
Box Solutions.
Αυτό θα είναι σαν ένα παράδειγμα, έτσι.
Τι,
Να πούμε για σαν ένα παράδειγμα ή...
Show right here.
Ναι, gas purification system. Καλά.
Για το βλέπω στα πίση δεν ξέρω τίποτα.
Alright. Please wait a second. The sound will be back.
Coatex Solutions. Εντάξει.
Είναι υπάρχει φωτογραφία εδώ πέρα εξάλλου, έτσι.
Ναι.
Τι δεν χρειάζεται να μπει μέσα.
Όχι, πρέπει να πούμε τους τομείς που μπορεί να απευθυνθεί. Και είναι αυτό, τα laboratory chemistry, batteries.
Alright. You're right here. Hi. So please introduce yourself.
Hello. My name is Panos Vounas. I am one of the owners of Vector Technologies Greece and the managing director. Our company is a test measurement company and was established as a major supplier of measuring instruments and high technology systems, specialized in sales, marketing and technical support and after sales services. We act as distributors in the Greek and the Cypriot market, and in some sections, like telecommunications, we are selling equipment to all Balkan countries. Our mission is to provide to our customers the most suitable solution for their specific requirements, always combining the highest the knowledge, the highest quality, and the most affordable prices. Our strategy is to work in cooperation with the world leading suppliers. Here you can find some of our partners. I'll tell you more about that in a while. And our facilities are located in Athens, in the Attica area. We are here in this exhibition to promote our products and to help our customers, the R&D labs, to find solutions and to work with our tools in order to make their research. We'll tell you more about in which sessions we can help. Yula is our sales manager for the R&D labs and the education market, and she will tell you more about the sessions that we can work for.
Hello from my side. Hi. One of our companies that is expert in this, let's say, part in this exhibition is M. Brown company, is a German company, who is present every application with inner atmosphere, required the inner atmosphere. So glove boxes and gas purifiers are the main, let's say, business of this company. So we can propose and actually discuss with customer according to their application and their needs, and to find the best solution for their needs and application. So the M. Brown, as I told you, have several applications. Is the suitable solution for several applications like laboratories and chemistry laboratories. A battery solution if you need personal protection from the material that you work with. OLED, organic electronics, weldings, material purification, thermal treatments, OPVs, and all these sections. So there are many glove boxes and many solutions like Lab Masters, Mini Lab, OPTI evaporation systems, and gas purification systems. Okay, so
many of our customers, they use the glove boxes,
yeah,
and they set inside their measurement tools. So, and they protect the material that the materials that they making are very sensitive. So they set inside the glove boxes the test and measurement equipment, or the spin coaters, or whatever equipment they need. So with this way they protect the material for the atmosphere. This is the general idea. On the other hand, Keithley, which is an electronics company, yeah, it's one of the, I think it's the leader of the test and measurement for the semiconductor characterization systems. Of course, we can talk the whole day here, but I think we give you a very quick introduction of the solutions that we can offer.
Yes, furthermore, we can say that we have service support. We can support our customers with services for as many years as required. And we are
here to support our customers.
Support our customers, yes.
Can you describe a little bit more what kind of customers you have?
The company
yes,
has three sectors. Mm-hmm. One sector, and this is actually what we are interested for at the moment, is the education the education sector, mm-hmm, which education means also R&D labs. As you know, many of the professors, they have their own labs, they make their own R&D, and we are happy for that because we have big, huge R&D in Greece, in the universities. So, education R&D lab is one section. Second section is the military and the governmental authorities. And the third is the telecommunication, which is mobile operators. But here today we are for the education and the R&D labs.
The R&D labs, yes.
And it's very advanced machines?
There are mostly advanced machines. We have educational test and measurement for the students, but all this that we mentioned before, it's for high-level, high-end equipment.
Yes.
And these companies, you have many years of connection with them?
Our company was established in 2006, and with most of them we work since then. Mm-hmm. We have long relationship, we have a partnership agreements, and we invest to that companies, and the companies invest on that, on us, because we need to train people, we need to have expert engineers, expert people who knows the products and know how to sell the product, and not only to sell, how to support, because the most important for us is the after sales support. Mm-hmm. To do a sale is the easy part, maybe, the most easy, but to keep the customer happy is the most important. The customer needs to have someone next to him in case he has a problem. Mm-hmm. So this is our role here, to support the customers after sales.
Mm-hmm. So it's very technical support.
It's technical support.
After sales support.
It's after sales support.
Say.
Maybe the customer needs some help on his application. Mm-hmm. So with this way, we will bring the specialist to provide the solution. Sometimes they have technical issues. We need to send a technician on site to repair the equipment. So it's a combination of R&D knowledge, of scientific knowledge and technical knowledge, let's say.
When you have, for example, brochures right here,
Yeah.
talks about perovskite solutions. It's like the trend for the most advanced. Is it just solar or many different things?
For perovskites, I think it's better that to let the professors to talk about that.
Yeah.
It's better to let the professors to talk about that because this is their job actually. We are here to offer the solution.
Solar machines?
Yes, this is the glove box, which use it especially for perovskites.
This is one of the solutions that M. Brown provided. Perovskite solution is one of the parts that M. Brown could provide.
For people who are doing perovskite R&D
We
in
can say
perovskite.
here that the first
Perovskite research,
yeah.
as you say.
The first meeting here with M. Brown was here some years ago,
Some years ago,
6
yeah.
years ago.
Yes, 6 years ago was our first contact with M. Brown.
With M. Brown here in this exhibition, Nanotexnology exhibition.
So it's a great place to network with the right people.
Exactly.
Yeah.
We were here at that period 6 years ago as exhibitors. At the same time, M. Brown was here as exhibitor. So we communicate with them and we realize that our partnership will bring growth to our market.
This is again the glove.
Yeah,
Yes.
the glove back
Machine.
solutions and many solutions that M. Brown can provide. There's gas purification systems, glove box solutions, all of this, gas purification systems, this particle removal. Electrolytic filling.
So it's people
Coating,
doing
sublimation.
R&D, people doing research,
Yes.
also people doing
Vacuum coating.
something that becomes mass production, big projects, pre-production of stuff.
Yes?
Yes,
Yes?
yes. Let's say a part of the production. Yeah. Yeah, many user protections. Okay, it depends on what the material that they have to work with. The customer wants to work with.
Glove boxes has applications not only in the nanotechnology or the perovskites, but also in the pharmaceutical area. Pharmaceutical companies also are using glove boxes for their applications.
So are there more and more customers, let's say? Like more and more?
Yes, more and more. There is a wide field
Yeah.
for glove boxes, wide field of
market,
applications
let's say, yes.
for glove boxes.
And sometimes there's an industry who realize that they didn't use it before, but they should use it now.
Of course, this happens because that's why we're here. That's why we're participating in exhibitions to show the customers what they need in order to make their life easier. Let's say.
Yeah.
And what kind of discussions do you have here at the Nanotexnology conference?
We discuss, actually here we meet the most of our customers because they are doing their R&D, so they discuss their application, so we have the knowledge to offer solutions, or maybe we can offer something that they haven't think so far that they can use it and they can make their research easier.
And your customers can be anywhere, or is this specifically in Greece, or?
M. Brown has customers worldwide, but we have the authorization to promote our products in our territory, which is Greece and Cyprus.
All right.
But of course, here is international event, international congress event, and of course we are happy to help any customer worldwide. And we will address his name and his contact to the right people so they can have a local communication.
And is there more and more high tech happening in Greece?
Of course, Greece there has, as I mentioned, a lot of many R&D labs, but we don't have many companies that they make productions. But we have, let's say, the last 3 years, you know, because of COVID situation, it was difficult to have face-to-face meetings and face-to-face and this kind of events. But I think now starts again, and we have more and more bigger events. I think this event here is the biggest one that happens every year.
What were you doing during COVID? You just do a lot of video chat?
We use a lot of video chat, exactly. Skype, Zoom, Teams, whatever. Of course, we had a lot of savings from the traveling. Of course, this is a joke. It is a reality, but on the other hand, we prefer the face-to-face meetings because it brings the relation with our people and our customers. It brings the relation. I feel better to meet someone face-to-face, let's say.
Nice. And people watching this might be interested to contact you. Just contact you and start talking.
Of course, they can. We will be happy to be in contact with people that they watch us and discuss their application and offer the solution.
Best solution
for them.
What if some new technology providers want to talk to you about distribution also?
We are happy.
And we are open.
And we are open to discuss.
Of course.
We are invest to relations, not only to sales.
Yeah.
All
And
right.
we're looking forward.
Cool. Thanks a lot.
Thank you.
Thank you so much.
All right. I'll put you on a break right now in the chat. See you in a minute. Please introduce yourself.
Yeah. Hello, you are in Nanotechnology 2022. I'm Kostas Simenidis, CTO of BL Nanobioment, and we are standing in front of the booth BL Nanobioment to introduce you our services, products, and generally what we do here and what we are about to present in this expo. So, first of all, BL Nanobioment is a startup that is dealing with high-tech, novel nanotechnology systems. What that means? That means that we are preparing technology and prototypes and then finally products for biomedical application, like biosensors that are in the category of in vitro diagnostics, like nanoporous materials or nanofilters, like nanoparticles that have specific properties.
I'm sorry. There's been a problem. Do you mind starting over? I think
No worries.
The video wasn't on.
Okay. No worries.
Okay. Let's do it right here. We'll cut it later. All right.
Just give me a minute.
I don't know. The PIP video was.
I don't remember the product.
Okay. All right. So please introduce yourself again.
All right.
Sorry.
Hello, you are Nanotechnology 2022. I'm Kostas Simenidis. I'm the CTO of BL Nanobioment. And we are sitting in front of the booth of BL Nanobioment to introduce you our company and our products here that we present here in this expo. BL Nanobioment.
It's great to be back, right?
Yeah. Sure. After COVID session, we are happy to see so many people around and to discuss about novelties and production. So, BL Nanobiomed actually is a high-tech startup company dealing with nanotechnology and biomedical application. What that means? What we do actually, we have innovative technologies like development and characterization of nanoparticles, development of biosensor platforms that they act as point-of-care systems to detect various diseases. We are preparing nanomaterials like nanoporous materials for filtering applications, like you want to filter viruses or nano-sized particles. And of course, our products for 3D printing that we can print in very high resolution 3D printed biospecimens. So, here you can see our product, which is a biosensor. It's based in a 3-electrode system. That means that you apply a sample and then it gives you a response. So let's come closer to see how this works. Let's say you have, actually this is about to detect troponin. What is troponin? A protein that informs the body about heart attack, if the individual is prominent to a heart attack. For us, this is very serious. So we have prepared this device. Again, this is prototype right now, which you can insert the strip. This is the bioinsertion strip. And when you apply some sample, let's say this is a blood or sweat, it gives you an electrical response like a number in milligram per liter. That means that we can develop biosensors to detect molecules in our body, like troponin. And this is our product for heart attack. An individual can take it from pharmacy and do the test in-house with not much money. He doesn't need to go to the hospital or to the diagnostic center to make a blood test, and he can get informed about if he is prominent for a heart attack. Then, BL Nanobioment can introduce our nanofilters Mr. Alexandros Orfanos he's the expert of the nanofilters. He can speak about this.
Hi. Hey. I'm Alexandros from BL Nanoenvironment. I'm a production manager and will present to you nanofilters. As Kostas mentioned before, BL Nanoenvironment is a high-tech It's a high-tech nanotechnology company in order to deal with unmet clinical needs. COVID-19 demands a big amount of need for filters. So our company focused to create these nanofilters in order to protect people from surpass the molecules, small molecules like viruses, to surpass the human body. Let's say some things about nanofilters. As you can see, we create a very thin layer which have a very density of very small pores in order to block the path of these particles. What is the advantages of the commercial filters? Commercial filters like HEPA or melt-blown have very big layers of these fibers in order to block the path. BL Nanoenvironment creating these nanofilters, creating these very thin layers in order to block directly the path of these particles. It's standard with mechanical properties without create a problem with the breath of the user, and as well have very different applications, especially in respiratory systems like this one, or different application in lab equipment, or dust treatment membranes, and generally the materials we can create on substrate in order to create an antimicrobial surfaces. This is the same technique. This technique uses a big manufacturing of using the same development like biosensor, like everything that we can mass production of that. What I want to say about that, antimicrobial surfaces can create a very exile environment for viruses and generally harmful molecules in order to stop them to evolve and have a very different application from very public uses. And other characteristic of that is generally then melt-blown. As I said before, we can enhance these materials over 10,000 because melt-blown has about micrometers in pores diameter, and we can enhance this blocking as well molecules like viruses. And
yes, so in overall, in BL, as you understand, we are dealing with difficult situations. As Alexis mentioned and me earlier, we try to apply technologies, of course, in nanoscale level. And why nanoscale level? Because in nanoscale you can understand what is going on and you can increase the specificity, sensitivity, or filtration efficiency, as he said. So as a conclusion, I have to mention that we are participating in many research, European and national projects to increase our R&D development. Here you can see two national projects that what we are doing here, we are developing nanoparticles to treat atherosclerosis directly in the vein. So in the first step, we prepare the nanoparticle, then we coat it, we encapsulate it, and then we put it in a demonstration like a bioreactor which simulates the human body, mechanical stress, and environment. So we can have a very good response on how these nanoparticles can go through in real-time situations. And another national project, this is we are trying to print bones, and this is very important. We have this machine which is a 3D bioprinting. We prepare the mold, then we prepare the biogel, and we incubate inside the mold and then into a bioreactor again to simulate the body response. So we are trying to fix, actually in dentistry, the bones that are broken or need to be replaced. So overall, that's all from us. Happy to be here in Nanotechnology 2022. Happy to have you here in our booth and explain in details our product services and generally what we do.
What is a BL rapid test based on nanotechnology?
Okay.
Have you been shipping a bunch of solutions? Or are you doing research for stuff that will happen in the future?
Actually, what it is, let's say that COVID just triggered this solution. We are trying to prepare rapid tests not only for COVID but for many diseases. This is a qualitative method, not quantitative as a biosensor to give you the number, but it gives you a signal that you have or you don't have a disease. So we have a versatile, universal platform that we can develop it tailor-made for whatever disease you want. And this is because of nanotechnology.
So when I look at right over there, it's like the circle of nanobiomed. You talk about the intellectual property, R&D, strategic collaboration.
Yeah, actually this is an overall of our company. We are trying to prepare nano-med products. We have our strong IPs. We are a part of many R&D projects with strong collaborations with IUth, OIT, many European universities and companies. We have a pioneer team of experts and expertise personnel. And finally, we try to find innovative solutions that are scalable and can go to production.
So nanotechnology has a huge place in the future of medicine.
I think so. So this is what we believe, that in nanoscale level you can find the answers that you can't understand in the micro scale.
All right, cool.
Thank you very much. Happy to be here.
All right. Well, thanks, everybody. I'll put you in a break for a minute. All right, there's a lunch break right now, so I'm going to put you on a break for a second, not for a second, maybe half an hour, 1 hour, and I'll be back with the afternoon live stream. So this stream is going to end. This was the morning live stream. So check back, like around in an hour, something like that. Continue for the afternoon. Thanks for watching.